the big thing about it, I would say, is that if you're scared of exponents, you're going to have a tough time. But once you get familiar with exponents, number 3 is actually relatively easy. So we have that a scientist is conducting an experiment on the growth of a certain species of bacteria. And so the population of the bacteria P can be modeled by the function blah. Okay? And notice they tell us a couple of things. On the one hand, we know that T is the number of hours since the experiment began, while K is simply a positive constant. They also told us, whoops, that the population of the bacteria is P. So remember, this P parentheses T, like its original version, is f of x. And so, basically, whatever's inside my parentheses is my x. So T in this case, so my x basically is going to be time. While my y is this whole thing. So f of x in its entirety right? However you say it, the whole thing is going to be y. Okay, so this whole thing is P for population. So my y in this context is simply population. That's the first thing we're going to point out. X is technically time, y is going to be population. So for part AI, we need to write down the value of P of 0. So if we're talking about P of 0, we're basically saying when x equals 0, what is y? Okay? That 0 right here is basically you're asking your function when x equals 0, what is your y? So when x is 0, well, you plug in 0 for x. In this context, x is time, my variable t, ¿cierto? So x is going to be my variable t, while my y is going to be my variable p of x, ¿cierto? O sea, p of t, sorry. Yeah, so P of 0 means I'm going to plug in 0 for t, so I end up with 1200 times k to the power of 0. Yeah, now anything to the power of 0, you guys, is simply going to be equal to 1. So 1200 times 1 is going to be 1200. Yeah. Now, I know there's more than one of you saying, huh? What the heck just happened? This is what just happened, okay? When you have, and this is what I mean, that this is a problem loaded with exponents. That this is going to happen a lot. This is the kind of thing you have to know, okay? Let's say you have 2 to the power of 3, okay? 2 to the power of 3, if you do some quick maths, it ends up being 8. Because, 2 to the power of 3 is 2 times 2 times 2. 2 squared is 4 because it is 2 times 2. 2 to the power of 1 is simply 2 because, well, it's simply 2, ¿cierto? And 2 to the power of 0, well, you got taught in school that anything to the power of 0 is equal to 1, so you're going to put it as 1, yeah? Now, right here, ladies and gentlemen, there is a sort of pattern that we can identify, okay? Technically, if I were to go from 2 to the power of 1 to 2 to the power of 2, well, what do you have to do? You can think about it as plus 2, but this is not a pattern that's going to work because 4 plus 2 does not give you 8. What you can consider, however, is multiplying by 2. So 2 times 2 gives 4. 4 times 2 gives 8. And the same pattern is going to happen over here. So 2 to the power of 4 has to be 8 times 2, which gives 16. And it does check out. Now that makes a lot of sense, but what if I tell you, okay, now go backwards? So if you were to go backwards, 16 divided by 2 gives you 8. 8 divided by 2 gives you 4. 4 divided by 2 gives you this 2, and 2 divided by 2 gives you 1. And so this is a pattern that will always occur. You have 3 squared, it's 9. You have 3 to the power of 1, you're just dividing by 3, you end up with 3. You divide by 3 again, and 3 to the power of 0 has to equal 1. And so the pattern that is arising here is that eventually you have your base number being divided by itself. You eventually end up with 2 divided by 2. or 3 divided by 3, etc., etc. That's why it's always equal to 1. The other way you can sort of try to remember it, or if you're a very visual person, you might recognize it, is that technically in the world of math, you always have a times 1, just like hidden everywhere. See, so you have a times 1, here you have a times 1, here you have a times 1, and eventually you're going to realize, so when you have 2 to the power of 0, instead of having this 2, you only have the times 1. See? Yeah, so that's another way you can sort of think about it, right? So this 1 means that you have 1, 2. This 2 means that you have 2 2s. This 3 means that you have 3 3s. This 4 means that you have, 3 2s. And this 4 means you have 4 2s. Okay, so 2 to the power of 0 means you have no 2s, so you have only the times 1. All right, I explained why anything to the power of 0 is equal to 1 in like a million different ways. So one of them must have convinced you, and now you understand that, okay, so this to the power of 0 has to equal 1. For part A, P of 0 equals 1,200. And for part A, I, we need to interpret what this value means in this context. Now, first of all, I will mention that this is a classic. Okay, they love asking when x is 0, what is y, and what does it mean? Okay, I've seen this a lot in IB exams, so focus on the approach. Okay, the first thing is really consider, okay, here I plugged in x equals 0, and my x is time. So when time is 0, well, what does it mean? Well, time in this context is number of hours since the experiment began. So if x equals 0 or my time equals 0, that means that my experiment hasn't began yet. Or it's like at the first second. You can think about it that way. See? So before this starts at all, when x is 0, my y is 1,200. Okay, but what is your y? Your y is population. So, clearly in this context, we would say that the initial population is 1,200. Okay, and you know it's initial because time is at 0. Basically, we are at the start of the experiment. Okay, and if you look at the answer key, it's something very similar to that. Initial population of the bacteria. So the big word you have to go for here is initial. You know it's initial because time is at 0. Okay? All right, enough blah blah. That was for part A. Then we have that 3 hours after the experiment began, the population of the bacteria is 18,750. And through this, we need to find the value of K for part B. Now, the big thing about these sort of word problems is that you need to bring these words into math. So this line of information that I am now putting in pink is very important that we understand it. Okay? Now, what is the main way to help you understand these sort of exercises? You have to write somewhere what I did up here. You have to have very clear what is your x, what is your y. So x is time, y is population. So if here we're talking about 3 hours after, then boom, immediately you say, this is telling me I have an x of 3. As simple as that. And y is population, and here they tell me that we have a population of 18,750. So y is 18,750. Now, just to be very clear in this sense, that means I have the set of points that when x is 3, y is 18,750. That's what it's telling me. Okay? So this thing in pink is basically giving you these coordinates, these set of points right there. All right? And through this, we need to find the value of K. Now, how in the world would this help me find the value of K? There's two main things I'm going to say here. The first one, is that when the IB gives you something, you have to use it, so just plug it in. Honestly, when the IB gives you something, you always have to use it. If you're in the doubt of what to do, just plug it into your equation and see what happens. And the second thing I'm going to mention, which is the more big brain approach, is right now, if I were to find the value of K from here, right, I am facing the following issue. okay? If you try to find the value of k from here, you technically have three variables, okay? Technically, you have your x variable, which is t. Technically, you have your y variable, which is pt, and you have your k, all right? So even if you try getting k alone from here, you still have two other variables going around being annoying. But if you were to plug in a set of points like this that I have right here, if you plug in a set of points, then boom, you fill in something for t, which would be 3, and boom, you fill something in for y, which would be p of t, which would be 18,750. And so suddenly, you go from having, and this is the big play, so you go from having, oh, that's very, I can't see that well. You go from having 3 variables to having 1 variable. That's the big brain play that's happening here. When you plug in the point, you go from 3 variables to having 1 variable. And if you have only 1 variable, you can reach k equals an actual value. See? Otherwise, you would be reaching k equals something something x, something something y. Not good enough, right? For finding the actual value of k, you need to get k alone. Plugging in a point helps you get k alone. Okay, that's the main message I'm trying to transmit to you. So if I go ahead and plug in k from here, let me just, there's a lot of space here. So for part B, my equation is P of t equals 1,200 times k to the power of t, right? And so part B gave me the information that I put earlier in pink, the set of points, 3, 18,750. So if I plug this into my equation, what I end up with is that 18,750. Remember that P of t is simply your y, and so this is your y, this is your x. In this context, again, this is your x, and this is your y, the whole thing, ¿cierto? Yeah. So if you go ahead and plug in, you end up with 18,750 equals 1,200k to the power of 3. Yeah. So in order to get k alone, well, there's two things that are I can't English today. There are two main things that are annoying you. So the first thing that annoys you is the 1,200, and the second thing is the exponent to the power of 3. Yeah. So for now, we're gonna deal with the exponent last because no one likes exponents. Okay. So first, get rid of the 1,200. It's multiplying the k, so we will divide by it. So that means I end up with k to the power of 3 equals the 18,750. The 18,750 divided by 1,200. There you go. So k cubed equals 15.625. And from here, well, how do you get rid of a cubed exponent? Or, sorry, a variable that is cubed, k to the power of 3. What the heck do you do? Yeah, first of all, if this exercise was a lot more simpler, we would have k squared equals 15.625. Okay, this is just an example for the approach. See? So in my example, I have k squared instead of k to the power of 3. And from here, you probably know what to do. You would look at this and say, easy peasy. All you gotta do is do a square root onto both sides. This goes away with this, and you end up with k being equal to square root of this guy here. Fair enough. From here, you can't exactly square root because, I mean, you can square root, but it's in a different way. Okay, and that's the thing that I'm going to try to explain here. Technically, the example on the right, it works because when you do square root, what you're asking, okay, in terms of math, is which value multiplied by itself gives you what's inside. ¿Cierto? That is why square root of 4 is 2, because you're asking, right here you're asking, what number times itself gives you what's inside. 2 times 2 gives you 4, so square root of 4 has to be 2. That's also why square root of 9 is 3, because 3 times 3 gives you 9. And so square root of x squared, well, with what thing multiplied by itself gives x squared? X times x gives you x squared, ¿cierto? So x squared sorry, I should have explained it like this. So x times x gives you x squared. So that is why square root of x squared is simply x. That it? Now, when you have it to the power of 3, it's still the idea of the square root, but it's a little bit different. The idea is the following. When you're doing square root up here, we know we're thinking about any number or value or whatever multiplied by itself twice. Multiplied by itself twice because technically in the world of math, there is a hidden number on your square root right about here. So there's a hidden number that we don't write it because we just assume it's there, okay? And this happens a lot in math. See, it's a little bit like, I don't know, you have x squared plus 3x plus 4. Everyone knows that this x is to the power of 1, but we don't write it because it's redundant, because it's obvious. The same thing happens with square root. All of these have a little 2 inside of them because this is telling you, yo, I am asking in terms of math, which number multiplied by itself 2 times gives me 4? Which number by itself multiplied 2 times gives me 9? Which number by itself multiplied 2 times gives me x? ¿Cierto? X squared, sorry. So that is why when people, or in your math class, your teacher wrote something that looks like this, he answered 3. Because 3 times 3 times 3 gives you 27. 2 times 2 times 2 gives you 8. And so this means that. So if you want to get k cubed alone, all you have to do is apply like the square root, but you're going to be doing it thinking with a 3 right there. Okay? That's the most intuitive way I can explain it. So k cubed, this goes away with this. K has to equal this square root with a little bit of a 3 outside. That it? Now you might already be thinking, dude, how the heck do I do that? Okay? Well, of course you have your calculator, don't freak out. Yeah. Clearly you're doing a very mathy thing, so we will be pressing the math button. Okay, you press the math button and look at that. It's right here. So this is square root when we're dealing with like a cubed. 15.625. Go ahead and enter. That is k. K is plus or minus 2.5. See? Plus or minus because we're talking about a squared square root. Technically, negative 2 times negative 2 can also give 4. ¿Cierto? Negative 3 times negative 3 can also give 9. But sorry, my bad. Because it's 3 times, it has to be positive. Yes or yes. See? Because if it's negative, it would end up as negative. Sorry, that might have confused some of you unnecessarily. Just leave it as a positive value. See? Whenever we're talking about cubed, it's got to be positive. Yeah. So k equals 2.5. And another way to sort of conclude that is that they also tell you that k is a positive constant. See? So, okay, whatever. K has got to be positive. That it? So the value of k following that is 2.5. We can see the same over here. So you can keep believing in me. I am not lying to you, at least not today. Yeah, then they tell us that the population of the bacteria, sorry, they ask us to find the population. Okay, so what is y of the bacteria 1 hour and 30 minutes after the experiment began. So what is y when x is an hour and 30 minutes? Okay, how do you express an hour and 30 minutes in terms of x? Okay, your x, we said, was time. Time as in t, by variable t. And t is in minutes and seconds. What's happening? It's in hours. So, an hour and 30 minutes, there are 60 minutes in an hour. So an hour and 30 would mean we have 1 hour and a half. All right? All right, awesome. So when x is 1.5, what is y? See? So my OG function is right here. P of t equals 1,200. And now I have k, so I'm going to plug in k. So k is 2.5 to the power of t. So right now, all I have to do is ask my function, when x is 1.5, what is going to be my y? So when x is 1.5, what is going to be my y? So that looks something like this. Okay, obviously it looks nasty. No one likes exponents, but we can learn them and make it a little bit easier on ourselves. So go ahead, plug it into your calculator. You end up with this. So P of 1.5 equals 4,743.41649. If you would like to leave it in significant figures, I guess you could count 1, 2, 3, round it up or keep it the same. You keep it the same, so you can leave it as 4,740. All right. Over here, either works, right? On the left, we have significant figures. On the right, we have the full number. Do as you please. That is for part C. All right. So just a quick disclaimer. You guys have probably realized by now, a lot of this is just understanding when to plug in X, when to plug in Y, and what to do from there. I insist, write down what X is, write down what Y is. It'll be much easier to understand what to plug in. See? So, following that idea or that concept, we have that. The scientist conducts a second experiment with a different species of bacteria. The population of this bacteria, S, can be modeled by the function blah, blah, blah. So once again, we do have that T is the number of hours since both experiments began. So again, in this context, we have that my X is going to be time. We're talking about the variable T. And that Y, again, is going to be population. Just that in this case, is the population of the second experiment, so it's going to be S of T. All right? All right. For part D, we need to find the value of T when the two populations of the bacteria are, notice, are equal. Okay, this is the big buzzword we will be talking about for now. So when two things are equal, what are they doing to each other? They are intersecting. When two things are equal, they intersect. Okay, and when two things are equal, they are literally equal to each other. So if we have to, this is like the big mathy way to do it. Dale? You need to find T when the two populations are equal. So if the two populations are equal, then that means that P of T, which is my first population, has to equal the second population. Now, if I were to plug in P of T and S of T from here, well, we know that S of T is this guy. So that means I can immediately plug in like this. This is a times, this is a decimal. And we also know that P of T is this. Well, with the K, it would actually look like this right here, okay? So, if I now plug in P of T and S of T, I end up with 1,200 times 2.5 to the power of T equals 5,000 times 1.65 to the power of T. So this has been my line of logic, okay? This has been my procedure. We need to find the value of T when the two populations are equal. So look at this. Here's population 1, here's population 2, and I am equaling them to each other. I equal them to each other. Well, what is P of T? I have that right here. What is S of T? I have that right here. Bada bing, bada boom, plug in both, and here we are. Now, of course, this looks absolutely nasty, and this is what I meant earlier by if you don't like exponents, you're gonna have a fun time. Yes, this looks like horrifying, but the one good thing about this, you guys, is that technically on both ends, I only have the variable T. So if you only have the variable T, you just gotta find a way to get T alone and solve from there, right? Now you could try to solve it using logarithms, getting the T out of the exponent and stuff like that. But the main thing I suggest for these scenarios, especially for when you have a variable on top of an exponent, I highly suggest you use calc intersect, okay? That is the main tool I will show you now. When you have a variable on top of an exponent, calc intersect does wonders for you, because you either use this tool here or you have to use logarithms, and no one likes logarithms, okay? I'm just being honest, all right? So When I talk about calc intersect, I'm talking about the graphing calculator, okay? Now for calc intersect, you do have to graph your lines first. So quite literally, this will be y1 and this will be y2. When I say y1 and y2, I mean about the y1 and y2 that you plug in into your y equals. So if this is y1, 1200 times 2.5 to the power of t, or by exponent, and the y2 is 5000 times 1.65 to the power of t, or my variable, ¿cierto? It looks like that. All right, cool. So if you go ahead and graph and you do calc intersect on both of these, you're gonna find whatever t makes this work, okay? Now, there's probably some of you that are a little bit confused by this. See, as I said earlier, when two populations are equal, they are intersecting each other, ¿cierto? So wherever they are equal is wherever they have to be intersecting, right? And so think about it this way. Wherever they intersect, they equal each other. So at the intersect, the value of t that we find is the value, is the moment in time where the populations are equal to each other. Okay, that is like the big brain play. All right, and this is mainly legal because these two variables are the same. Okay, if one of them was x and the other one was y, well, graphing it would be very, very different. Okay, but because they're the same variable, you can use calc intersect safely. All right. So I tried graphing it. It looks like this. Yours probably also looks pretty terrible, right? So all you need to do is find the intersect. Now on my window, I cannot see the intersect. So what I'm gonna do is go to zoom, go all the way down and press zoom fit. Zoom fit a lot of times helps you see the intersect. Other times you press it and nothing really happens, or it doesn't really help. But let's see if in this case it does help. All right, there's one of my lines. Oh, look at that. That seems to be the other one. All right, so judging from this, I probably have an intersect that I can barely see that's down here. See? So just to make sure that I can see it better, I'm gonna be changing my window. Now, for example, all these x values on the negative side, you do not care about. You do not care about negative hours on your experiment. You only care about from 0 and beyond. Quite literally, you only care about from 0 and beyond. Okay? So on the one hand, you can change your window to have no negative values, but yes, positive ones for x. And my y min, just so that it looks a little bit more pretty, I'm going to leave it as -1. ¿Cierto? My y is my population. And if my initial population of one of these is 1200, right? From the context from part A, II, well, then my y max, we can probably leave it as 10,000, right? That sounds about right. So that's the kind of details and stuff you gotta watch out for in order to get a much nicer window. So now I'm gonna try graphing again. There's my line in red. Now, as you can see, I still cannot see the intersect, and I'm glad this is happening because it's a good example of how it really is when you solve these problems, okay? It really is when you solve these problems, you're gonna be fighting with the calculator a lot. You're gonna be fighting with the window a lot. So get used to these tips and tricks in order to like get a better window. See, a lot of times people do well in this test only because they're good at handling the calculator. Like, I'm not even kidding. If you're good at handling the calculator, you can solve this way, way faster. See? So one way to solve this way, way faster is make this y value much bigger. And yes, end up with a graph that probably looks a lot uglier, but you will be able to see the intersect. And that, ladies and gentlemen, is all you really care about. See? It actually ended up being a pretty graph, but point is, put in big numbers. All you need to do is be able to see the intersect. Okay, you don't need a pretty graph. You're not drawing this or whatever. You just need you need to be able to see the intersect. That is, so plug in big numbers, plug in the values you only care about. You don't care about negative values in this context. Get a good window so you can calc intersect quicker. All right, so from here you do calc intersect, so you gotta press second and trace in order to hit calc, go all the way to intersect, see what it asks for. It first asks for your first curve, see? So go to the left, go to the right. All right, clearly my first curve is this blue one, perfect. And my second curve, voila, it's my red one, see? Always double check because sometimes people press downwards and the first curve ends up being the same as the second curve, or vice versa. See, so make sure you double check that you're doing this correctly. First curve is blue, second curve is red, enter, enter, and here you have guess. Now your calculator is not dumb, it knows where to guess. The guess function only helps if you happen to have more than one intersect. Anytime the calculator has a guess thing, it's really asking you which intersect do you want. So clearly I want the intersect that we can see on screen. You press enter. There it is. So again, when they intersect, they equal each other. So at the intersect, the value of t that we find is the moment in time where the populations are equal to each other. And also the population we get. So using calc intersect, you end up with 3.4345687. Did I get that right? 434.5. Wow, I've got some good memory. And the next one, let's see if I can get it to 27,921 167. 167. All right, awesome. So this, using calc intersect, we end up with these values. See, so this is my point. When they intersect, this is a point of intersection. So in other words, the populations are equal to each other right after like 3 hours and a half, sort of, ¿cierto? And what population do they both have? They both have a little less than 28,000 bacteria, okay? That is how you interpret for part D. So for the value of t when the two populations of bacteria are equal, you can just put in your x value because x, as we said, x is going to be time. All right, so the value of t is the x value of my intersect, 3.4345687. If you want to leave it in significant figures, you just gotta count 1, 2, 3, round it up or keep it the same. You keep it the same. So t, you can also leave it in significant figures as 3.43. Don't forget your units, hours. If we go over here, all good right there. All right, so notice for the method point, all you have to do is equate p and st, see, which is literally what we did right here. And then how to solve it, well, it kind of leaves it up to you. And calc intersect for me is the friendliest. All right, so I hope it helped. That would be for part D. All right, only 2 more parts, you guys. Hang in there. Then they tell us that it takes 2 hours and m minutes. So 2 hours and m minutes for the number of bacteria in the second experiment to reach 90,000. And through this, for part E, we need to find the value of m, giving your answer as an integer value. The first observation I'm going to do is that for part E, you need nothing from part D, nothing from part C, nothing from part B, nothing from part A. And this is a classic for paper 2. Paper 2 oftentimes mixes 2 problems into one question. Like from A to D, it's its own thing, and from E to F, it's probably going to be its own thing as well. See? So if you're having trouble from A to D, be on the lookout for these kind of switches. Here it's only talking about the second experiment, so you don't care about the first. You can probably solve it without having to do, without using anything from A to D. So keep that in mind, you guys. If you're clawing for points, that can be a good test-taking strategy. All right, realize that there are 2 exercises within one, and you can skip the parts to get points wherever you can. See? Maybe another test-taking strategy is realizing, this is worth 4 points. So maybe I might as well invest my time there. You don't need parts A through D. Maybe you want to start there. I don't know. I'm just saying that's a kind of tip or trick that can give you those extra points that you might need. Yeah, so once again, they give you a Y of 19,000, see? And the X, they sort of give it to you. They tell you it's 2 hours and something. So you know that X is 2 point something. Okay? So really all you have to do from here is just find, plug in Y equals 19,000, find your X, and figure out how to give your answer as an integer value. Just a quick reminder, when we talk about integers, you guys, it is simply whole numbers. Positive and negative. So integers will be -3, -2, -1, 0, 1, 2, 3. Right? Integers are whole numbers. If we were talking about, I don't know, natural numbers would be all of these except for the negatives. Okay? So keep that in mind. Integers is just whole numbers. You don't want a decimal here, you want a whole number. So for part E, all I have to start off with is that my population is 19,000. So my second equation is S of t is right here, right? So S of t equals 5,000 times 1.65 to the power of t. So if they tell me that my population is 19,000, well, what does t have to be? ¿Cierto? So 19,000 equals 5,000 times 1.65 to the power of t. Now, once again, I'm facing the issue where we have a variable on top of an exponent, so I can do calc intersect once again. So I can call this y1, I can call this y2. The procedure is the same, okay? So from here, well, y2 is already written in. I just gotta change y1 to be 19,000. The window is probably gonna be okay, so let's go ahead and graph. There's my y1. It's a horizontal line, makes sense. There's my y2. See? It's a horizontal line because all these different points are different x's, but with a y that is always 19,000. So here is my intersect. Just gotta do calc intersect. I already explained all of this. So this is your first curve. This is your second curve. Guess anywhere because there's only one on screen. There it is. So the intersect we got, ¿cierto? From this was 2.665, 8685, comma 19,000. Alright, you guys, so this is the amount of hours. See, so technically I have 2.665865 hours. Now what they want us to answer is to answer with hours and minutes and leave it as an integer. So technically, if I were to like spread this out a little bit, you end up with 2 plus 0.6658685, right? Now this is in terms of hours, and this is also still in terms of hours. If I wanted to pass this to minutes, well, what do you have to do? Clearly, the 2 hours, all you have to do is multiply by 60 because there are 60 minutes in an hour. So if you do 2 times 60, you end up with 120 minutes, right? So the 2, if I were to pass it to minutes, from 2 hours to minutes, and it ends up as 120 because you do times 60. And this, if you were to pass it to minutes, you also do times 60. Ah, okay, that makes sense. So 0.6658685 times 60, there it is. So that would be 120 minutes plus 39.9521. 1 minutes. See? Now, because they wanted as an integer value, we will be rounding up using significant figures and stuff like that. And so clearly, my biggest integer from here, I gotta compare the 9 that's next to the decimal. So this guy, do you round it up or keep it the same? You round it up. So if you were to leave it with integers, you can leave it as 120 plus 40 minutes. See? All right, so in this context, so it's 120 plus 40 minutes. That means that it's 2 hours. So it's 2 hours plus 40 minutes. And what they were asking for earlier is they know it's 2 hours and m minutes. And so through here, you just found out that m has to equal 40. And if we check over here, they do seem to agree with us, 40 minutes right there. There is more than one method. The most important one that you will see anywhere though is first trying to find out what the heck is going on with t, or replacing t with some other thing, etc. See? So ours was method 1. First we found our value for t, and then we gotta multiply by 60 in order to convert it to minutes. So remember, 1 hour is 60 minutes. That's the big thing you have to know. That is not in from a booklet, but you should know by now, okay? All right, so there you go. That is for part E. Last but not least, they tell us that the bacteria in this second experiment are growing inside of a container. The scientist models the volume of each bacterium. So on the one hand, we have the volume of each bacterium in the second experiment to be this. And also the volume inside the container, so volume, is going to be that. Okay, so one is the volume for the bacterium, one is the volume for the container. Let me color code this a little bit better because it probably will be more important. So one of them is volume for, what's in green is volume for bacterium, while what is in blue is volume for the container. And so for part F, we need to determine how long it would take for the bacteria to fill the container. Now, this is way easier than what you think, but I need to explain one or two things before that. See? What's probably happening to you right now is that you're looking at those numbers and you're saying, what the heck even is that? See? Guys, whenever you see something like this that is 10 to the power of something, especially if it has a negative exponent, ¿cierto? Here we have what we call scientific notation. So first, let's make this a little bit more friendly, okay? The cool thing about scientific notation and why people do this is because this number has a lot of zeros. See? This one also has a lot of zeros. In fact, if you were to put that into your calculator, it's 2.1 times 10 to the power of -5. Not even your calculator likes putting in the zeros. See? What's happening here, technically, right? Let's go piece by, let me explain this in a different way. See? Imagine this was only 2.1 times, just so that we understand what scientific notation does. ¿Vale? Imagine you have that 2.1 and you only do it times 10 to the power of -1. ¿Vale? So if you have that 2.1 and you multiply by 10 to the power of -1, really focus on the decimal. So here we pass from having 2.1 to having 0.21. And if you were to do the same thing again, right? If you take this and multiply by 10 to the power of -1, you move the decimal place again. So each time you multiply by 10 to the power of -1, you're moving over the decimal place. So if we have 2.1 times 10 to the power of -5, technically you have to move the decimal place 5 times to the left, following the pattern I just showed you. So moving it 5 times is 1 time, 2 times, 3 times, 4 times, and 5 times. So your decimal place would end up here. That means you end up with 1 0, 2 zeros, 3 zeros, and 4 zeros. Got it? Well, technically the initial 0 point something. See? So from here, what you end up with is actually that 2.1 times 10 to the power of negative 5 has to equal 0.000021. Okay, that's the first thing we're going to talk about. This, in terms of scientific notation, you can just rewrite it like this. It's a lot friendlier. I suggest that you do that. See? So this is going to be for volume container. So the volume of the container is simply this number here. Let's follow the same idea, but for the volume of the bacteria, we need to move the decimal place 18 times. Okay, that's definitely a little bit annoying, but at least visually, so that we're all on the same page, I'm going to go ahead and do it. See, so if you have 1.0, that's it, and you do this 18 times, you end up with 1 time, 2 times, 3 times, 4 times, 5 times, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Here's the decimal point, and technically a 0 initially. See? So it's going to be 0.00000. Okay, clearly you're probably thinking, man, it's crazy to do it this way. Why is this guy doing it this way? I'm doing it this way so first you understand what scientific notation is doing and why people use it in the first place. That is, so your actual number for the volume for bacteria is simply going to be this. Okay, so let me put that as 1. So this is your volume of the bacteria. All right, so I'm doing this just so that it's more friendly for us to understand what scientific notation is actually doing. That it? Now, for part D, let's come back to reality. They're asking us to determine how long it would take for the bacteria to fill the container. And so the first question you have to ask yourself before that is, how many bacteria fill a container? So if you find out how many bacteria fill a container, you can use that information to plug it into S of t with y, ¿cierto? And that gives you x for time. So that's a game plan. How many bacteria fill a container gives you a y. Plug into your equation, you get an x. And the x is determining how long, so x is time. ¿Vale? So that is my game plan. This is what I'm going to be doing. ¿Vale? So how many bacteria fill a container? Well, clearly, all I have to do is take the volume of the container and divide it by the bacteria. And that will give me the amount of bacteria that fill in the container. Now, I could take my calculator and plug in some very long numbers. For example, this is the volume of the container, 0.000021, divided by the volume of the bacteria, which is 0.000000000000000001. Okay? And there you go, right? Not the most exciting thing in the world. We could have just done this with scientific notation, but I did write all the zeros out so that we all understand what it does. Okay, I know that for a lot of you it's new, maybe you haven't seen it, so I'd rather explain it first like this. Of course, the smarter way to do this is to simply leave it in terms of scientific notation. See? So this would be the volume of the bacteria, and that is what's going to be divided by, sorry, the first parenthesis is the volume of the container, and that is going to be divided by the volume of the bacteria. See? So just so that you guys believe me, here it is, and it gives you the same answer. Okay, so scientific notation, why do people use it? So that you don't write 0 a bunch of times. I wrote 0 a bunch of times so I could teach it to you more, fluidly, and that's the main idea. But really, you can treat these as numbers anyways, with the exponent and everything. Dale? So, how many bacteria fill a container? Clearly from this, you discovered that we got a really big number. See, so 2.1 times 10 to the power of 13. Now it's a positive exponent. So if before I was moving my exponent to the left, ¿cierto? I was moving it to the left in both cases. Now I gotta move it to the right. So 2.1 moving it to the right 13 times is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what you actually end up with is a number whose decimal place has now moved all the way over here. That is what's happening. See, this is the amount of bacteria it takes. This is the amount of bacteria you need in order to fill in the container. Got it? So you can plug in all the zeros, but for now I'm going to just plug in terms of scientific notation. I did that for you to understand what is happening behind the scenes. Dale? So this is the amount of bacteria you need to fill in a container. So technically, if I plug that into S of t, ¿cierto? We know that S of t is this. So if I plug in 2.1 times 10 to the power of 13 equals 5,000 times 1.65 to the power of t. Now all I have to do is find t from here, and I will have solved the problem. Now, once again, I have a variable on an exponent, and the tool that I taught you is calling this y1, calling this y2, and seeing what happens. So we go to y equals, y2 is already y2, y1 now has to be this big number that I will put it in scientific notation because it's perfectly legal, and it's much better than writing a 0 a bunch of times. Go ahead and graph. I'm probably not going to see the intersect. My window is probably too small. Yeah, it really seems like my window is too small. So, much like before, first try zoom fit. Sometimes you one-shot it like that. Sometimes you don't. Let's see if it does. I think it might. There's a good chance it might. Damn. All right, well, my line in blue is my y1 and my line is red is my y2. So probably what I gotta do is give it a bigger x. See? So if I go ahead and plug in a big x, like, I don't know, whatever, 50. Maybe now it works. Let's see. Oh, there we go. See? Now, this is a great example of a graph that looks terrible, but a graph that gives you the intersect anyways. See, so this might look very ugly, but all we care about is seeing the intersect, and we do. We can barely see it, but we see it. So here you can do calc intersect. There you have your first curve, up top the one in blue. Here you have your second curve, the one in red. Here it asks for guess. There's only one, so you can guess anywhere. And there it is. So when you did calc intersect, you ended up with 44.24 8091, comma, your y1. See? So clearly in this context, my y was my population, my x was my time. Here they're asking for how long it would take. So they are asking for my x. See, so the x in this context is this number here. So that is your answer for part F. For part F, you just got to plug in that number here. Technically, if you want to leave it as significant figures, you can count 1, 2, 3. Round it up or keep it the same. You keep it the same, so you can leave it as 44.2 hours. If I show you the answer key, there it is, 44.2 hours. All right? So, as you can see here in the answer key, they do solve it, leaving it in terms of scientific notation. I did first have to explain what scientific notation was because I'm sure some of you had no idea. Now that you know, you can safely calculate it. For example, as I did over here, simply dividing them. Trust me, it's just a big number with a lot of zeros. As long as you're consistent, the answer will be the same. That it? So, ladies and gentlemen, that is for part F, and that is for number 3. I hope it helped, and I'll see you around.